you, Beppe, for the introduction. I'm happy to be here and to present this joint work with Ivan Di Liberti. The motivation stems from modal logic. So classical modal logic extends classical propositional logic by adding two unary operators, diamond that expresses possibility, and box. It is necessary that P, together with appropriate rules. Now, just like algebras of classical propositional logic are Boolean algebras, the algebras of modal logic are modal algebras, and these are a modal algebra is a Boolean algebra with a unary operation box that satisfies, well, that distributes over finite meets. So box of 1 is 1, and box of x meet y is box x meet box y. And diamond is definable from these. And I want to draw the attention on the fact that all the axioms are equational. So all the axioms of Boolean algebras are equational. And also these two axioms. Equational means we have an identity that is between two terms that is universally quantified. And this allows to use, so thus modal algebras form an equational class, so a variety of algebras. And so the powerful techniques of universal algebra apply. And I will come back to this point later. And to represent modal algebras, one can build on top of Stone duality. So Stone duality for Boolean algebras states that Boolean algebras can be represented via Stone spaces. So there's a dual categorical equivalence with compact Hausdorff spaces with a basis of closed open sets. And Johnson-Tarski duality uses this Stone duality to represent modal algebras, and they are dual to descriptive frames. So these are Stone spaces with a certain binary relation, so the accessibility relation that satisfies certain properties. And among these properties, we have that for every point of the space, the set of points in relation with it is closed. So an accessibility relation. So we can define a function from x to the set of closed subsets of x. And so an accessibility relation can be defined equivalently as a certain function from x to the set Vx, x, satisfying certain properties. Now, what are these properties? Well, they can be neatly described. If we topologize the set of closed subsets of x with the Vietoris topology, then R can be described as a continuous function from x to v of x. So these these properties here are equivalent to this function to be continuous. Okay, and so this brings us to the realm of coalgebras. And here, if you have an endofunctor, so just an endofunctor, on a category by a coalgebra, I mean an object x of C and a morphism f from x to f of x. So there's a natural notion of morphism of coalgebras given by this square commuting. And, well, the Vietoris construction gives rise to an endofunctor on the category of Stone spaces and continuous functions. And a descriptive frame can be identified, as we said before, with a continuous function from x to the Vietoris space of x. And this is just a coalgebra for the Vietoris endofunctor. So Johnson-Tarski duality can be described as follows. The category of modal algebras is dual equivalent to the category of coalgebras for the Vietoris functor on Stone spaces. Okay. Now, I'm interested in an extension of this duality from stone spaces, which are certain compact Hausdorff spaces, to the category of compact Hausdorff spaces and continuous function. And the Vietoris functor extends to an endofunctor on compact Hausdorff spaces. So the Vietoris space of a compact Hausdorff space is still compact Hausdorff. Okay, and by stone duality, the dual of the category of stone spaces is the category of Boolean algebras, which is a variety of algebras. So in particular, it's monadic over set. And something analogous happens for the larger category of compact Hausdorff spaces. The dual is monadic over set with a monadic functor given by the representable functor. For example, you can choose the unit interval, 0, 1. So compact Hausdorff spaces are dual to a variety of algebras. Infinitary, so there are operations of infinitarity. Okay, this was proved by Daskin. And now we are interested in lifting this to coalgebras, so to model logic. And so by what I said before, the category of coalgebras for the Vietoris functor on stone spaces has a dual which is the variety of modal algebras. So in particular, is monadic over set. Well, we can use the tools of universal algebra. And the question is whether also something similar happens for compact Hausdorff spaces. So if you take the coalgebras for this Vietoris functor, is the opposite monadic over set? So is it, or equivalently, is it dual to a variety of infinitary algebras? And so we would like to have a proof of this fact that uses categorical means rather than algebraic, taking an algebraic signature and equations, because we didn't want to commit to certain specific choices of the signature. And so, okay, so we use, the answer would be yes. And to do so, well, first of all, given an endofunctor f, we have a forgetful functor from the coalgebras of f to c. So on object, you take an object, so a coalgebra, and you map it to the underlying set x, object x. And so the strategy to prove that coalgebras of Vietoris op is monadic over set is to take this forgetful functor, show that it's monadic, and then compose it with this other monadic functor that we know from Daskin to be monadic, and then somehow prove that the composition is still monadic. Now, of course, usually monadic functors do not compose. I mean, the composition of monadic functors is not monadic, but under certain conditions, it is the case. So, and we use one of these sufficient conditions. So if f and g are two monadic functors, and the monad t on d that is associated to the first one preserves reflexive coequalizers, then the composite is monadic. Okay. And in our case, we are in this situation where we have the opposite of this forgetful functor. We want to understand when this is a certain composition is monadic, and this is the condition. So if f is a functor that preserves limits of omega cochains, so a chain ordered like the negative integers, and if it preserves also coreflexive equalizers, then for every monadic functor from from C up to D, the composite of this the forgetful functor and the functor G is monadic. So how do we use the hypothesis? So the fact that F preserves limits of omega cochains is used to prove that this functor has a left adjoint. Okay, now with the up, I'm getting confused. But okay, yes, as a left adjoint, and so is monadic. It's enough to show that it has a left adjoint. And also this hypothesis gives us a construction of the left adjoint, and we use this construction and the fact that F preserves coreflexive equalizers to prove that the monad on C up here preserves reflexive coequalizers. Okay, there's also a version with algebras instead of coalgebras, but we just needed this for coalgebras. And so we apply this to what we wanted. So if we take the opposite of the category of coalgebras for this Vietoris functor on compact Hausdorff spaces, this is monadic over set. And yes, we show that the hypotheses of the previous theorem are satisfied. Well, they were actually already been shown. And so this composite of the forgetful functor and of the Daskin monadic functor is monadic. And analogous results hold for certain variation on the Vietoris construction, namely the lower Vietoris and upper Vietoris. And also analogous results hold for positive modal logic. So positive modal logic is modal logic without negation. And it has some algebras, which are positive modal algebras. These are bounded distributive lattices with box and diamond and some equational axioms. We have a representation theorem for positive modal algebras that builds on Priestley duality. Priestley duality is a dual equivalence between bounded distributive lattices and Priestley spaces, which are certain stone spaces with a partial order. And similarly to the non-positive setting, positive modal algebras are dual to coalgebras for an appropriate version of the Vietoris functor on Priestley spaces. Okay, and just like stone spaces can be generalized to compact Hausdorff spaces, Priestley spaces admit a natural generalization to what are called compact ordered spaces that are a compact Hausdorff space with a partial order on it, and the partial order is closed in the product topology. And again, here we have an analogous of the Vietoris functor, and also again here the opposite of the category of coalgebras for this functor is monadic over set. So it could also be presented at certain algebras for an equational theory. And for this result, we use an analogous of Daskin's result, namely that the category of compact ordered spaces is monadic over set. Okay. So to sum up, we had these various Vietoris constructions, various versions of it, and we show that the opposites of the categories of coalgebras for these versions are all monadic over set. And we use categorical techniques to prove this instead of equational ones, so that we didn't commit to specific signatures and equations. But yeah, it would be also interesting to see what are certain natural axiomatizations. Okay, thank you.
Thank you, Marco, for your very interesting talk. And so, are there any questions, comments? Yes, I will bring the mic because we record your question.
It's a long shot, but do you know whether, in the case the monad comes from an operad, so the structure is quite simple, this is some kind of instance of a causalness, of kind of causal duality?
Can you repeat? I missed the first part.
If this duality is somehow related to the causal duality that you have for operads, algebra over operads, coalgebra.
Okay, I don't know. Thank you for this. Okay, I will write. Okay, can you tell me later?
Yeah, of course.
About this?
No problem. Yeah.
Okay, thank you.
Thank you for the question. And other questions or comments? I have one, maybe a question or a comment. I don't know. You decide.
Okay.
The fact that you use these such general methods to achieve your result make me think that maybe there is a general theory behind that connects monadicity and duality. Did you think about this? Have you in mind any broad generalization of this?
No, I don't know. I don't know.
Okay.
But if
I don't know either, but
Okay.
maybe we can discuss.
Yes.
Okay. Maybe it's a direction.
Okay. Thank you.
No. I mean in a general. Yes. Okay. Other question? Anyone? No. So let's thank Marco again.